Okay, so this is the last video for section 8.4, and it'll probably be a bit of a long one. Okay, so what we're looking at is to start to figure out how alpha, the significance level of a test, and beta, by which we calculate 1 minus beta, the power of a test, sort of play together. So why don't you pause, copy this down, and then press play. All right, so we're going to have a fair bit of algebra and some detailed thought work in this video. So our setup is going to be that x1 through xn are a random sample from a normal population where we know sigma. And then we know from Math 313 that the sample mean is also normally distributed with the same mean and a knockdown standard deviation. Now, our null hypothesis is going to be that the mean is equal to mu0. And the alternate hypothesis is that the mean is equal to mu1, okay? Where, just for make things slightly simpler, where mu1 is greater than mu0, all right? Now we're gonna look at a designated significance level that I'm not gonna set at 0.05 or anything like that. We're just gonna call it alpha, okay? So let's talk through something we've done many times or several times in examples in previous videos. Alpha, the significance level, by definition, is the probability that we reject the null hypothesis, given that the null hypothesis was actually correct, okay? So this is a false positive. Now, since mu1 is greater than mu0, I'm going to reject the null hypothesis when my sample mean is greater than some certain threshold, okay? The critical value. Given the null hypothesis, which is that the sample mean is actually normally distributed with a mean of mu0, and that's standard deviation, okay? I'm then going to do my standard thing. I'm going to subtract the true mean, divide by the standard deviation on both sides of there. The left-hand side is now a z variable, a standard normal variable, and the right side is that mess there, okay? So alpha is equal to the probability that z is greater than that mess. That would mean 1 minus alpha, the complement, the other probability, is the probability that z is less than or equal to that same mess, okay? And since z is standard normal, I can express this as just the CDF of the standard normal evaluated at okay? All right, now let's let Q be the 1 minus alpha quantile of M01, okay? So I've got that 1 minus alpha quantile, let's call it Q. So then I can simply say that Q is equal to C minus mu0 over sigma over M. So Q is the spot where the probability to the left of that spot is 1 minus alpha. And that spot we have calculated to be C minus mu0 over sigma divided by root M. So that's how I get to here. And then I can simply solve for C by multiplying sigma root N over to Q and adding the mu0. Okay? So there is a formula for the critical value under these assumptions, okay? So, for example, if alpha happened to be 5%, then 1 minus alpha would be 95%. The 0.95 quantile of the standard normal distribution is at 1.645. So that would be my Q value that I would set equal to this fraction. And solving, I'd have C being mu0 plus the 1.645 times sigma over root N, okay? So if you give me an alpha, I can now calculate the critical value based on mu0, sigma, which is known, and N, which is known, okay? Right, so basically the critical value is based upon the choice of alpha. Okay, so how does that impact the power? So why don't you pause, copy, and play. All right, well, the power is defined to be 1 minus beta. By definition, it's the probability we reject the null hypothesis when the alternate hypothesis is correct, okay? We'd like the power to be close to 1. We'd like this to almost always happen. If the alternate hypothesis is correct, we'd like to reject the null, okay? Well, rejecting the null hypothesis means that X bar exceeds that critical value C, which I have a formula for. And the alternate hypothesis being true means that my sample mean X bar is normally distributed with a mean of mu1. not mu0, but mu1, the alternate hypothesis, same standard deviation. All right, so I've replaced C with what we calculated in the previous panel. And then I'm going to standardize both sides of that, given the mean of mu1 and the standard deviation, sigma over root n. So I subtract mu1 from both of those and divide by sigma over root n. On the left side, that is now a standard normal variable z. And on the right side, I do some algebra. I've got mu0 minus mu1 over sigma root n. And then q times sigma root n over sigma over root n. Sigma over root n's cancel. I'm just left with positive q. Okay, so there's some algebra. Then I do a bit more algebra. I drag that minus sign between the mu0 and the mu1 out in front, making it negative mu0, positive mu1, or in other words, mu1 minus mu0. There's the minus sign that was dragged out in front. There's the q. So I have the power 1 minus beta is the probability that z exceeds this value, okay? So in other words, the power depends greatly on the value of this spot. If this value, q minus fraction, is really, really small, it's easy for a standard normal to be greater than a small value. So this probability would be higher, and hence our power would be higher, okay? All right, so this relationship is going to get featured on the next panel. Okay, we're going to talk about some consequences of that. Because remember, this is telling me my power 1 minus beta, and q was based on my significance level alpha. So we're going to see how those two interact on the next panel. Okay. All right. So here is where we really have to put on our thinking caps. Now remember, from the previous panel, the power 1 minus beta is the probability that a standard normal variable is greater than this quantity. Okay. So what impacts the power of a test? Pause, copy, and then let me talk through it, and probably pause, replay it a few times until it sinks in. All right, so what impacts the power based upon this relationship? Well, the first thing is the effect size. The effect size is, by definition, the difference between mu0 and mu1. In other words, mu1 minus mu0, okay? If this difference is large, we have a big difference. That means mu1 minus mu0 is a large number, so this is a large fraction, and q minus a large fraction is a much smaller number. And the probability that z is greater than a smaller number is much higher. So if you make mu1 minus mu0 large, you make this probability large, which makes the power large, which we like, okay? We want the power to be as close to 1 as we can, okay? So takeaway, as mu1 minus mu0 increases, the power also increases, okay? So if your alternate hypothesis is significantly different from your null hypothesis, you're more likely to have a high power as a result of that. Whereas if your alternate hypothesis, your mu1 is very close to mu0, it's going to make your power smaller. You're going to be less likely to correctly reject the null hypothesis, which kind of makes sense. If you don't differentiate yourself from the null hypothesis, it's more likely you can make mistakes, okay? All right, what also affects the power? The denominator, sigma over root n. Now, we can't control sigma. That's given to us in the population, right? But we can sometimes control n, how much data we gather. So as n increases, this fraction decreases. Now, if this fraction decreases, it causes this fraction to increase. Smaller denominator, bigger fraction. Now, if that entire fraction is bigger, then q minus that fraction decreases, it gets smaller. So if this quantity is smaller, it's easier for z to be larger than it. So that probability increases. That's the power, right? That probability is exactly 1 minus beta, the power. So the take home was, as n increases, the power increases, okay? So you want your test to have a larger power, gather more data, and sometimes you can control that, right? Okay, the other thing that impacts the power is the significance level, that alpha, okay? Now remember, so let's talk through it. If we increase alpha, alpha was the chance of committing a type 1 error, incorrectly rejecting the null hypothesis, rejecting it when it turned out to be true. If you're willing to have a higher chance of that type of error, if you're willing to increase your alpha, then what happens? If alpha gets bigger, 1 minus alpha gets smaller. Like if that moves up from 0.05 to 0.1, this goes from 0.95 down to 0.9. So 1 minus alpha decreases. If 1 minus alpha decreases, so does the quantile it corresponds to. The 0.9 quantile is to the left of the 0.95 quantile for N01, right? So Q decreases. If Q decreases, then this subtraction or this difference also decreases. A smaller value minus the same fraction here becomes smaller than it was before. And if that quantity decreases, it's easier for Z to be larger than it, so that probability increases. And that's the power. So take home, increase alpha increases the power, okay? So if you're willing to have a higher chance of committing a type 1 error, you're going to have a better chance of correctly rejecting the null hypothesis as well, all right? So it's kind of a push-pull. If you're willing to commit more type 1 error, you're going to have a higher power as a reward. And that might be good, it might be bad. Okay. All right. So this tells us that alpha and beta are both linked. Now, in general, statisticians seem to enjoy having a power that's at least 0.8. Okay, so that's sort of like the threshold for a good statistical test would have that kind of a power. All right, so last panel for section 8.4. In 8.4, we've talked a lot about critical regions and critical values, and now let's sort of relate it to p-values if we can. So pause, copy, and play. All right, so how do p-values and critical regions or critical values play with each other? Well, a couple things to remember. When we computed p-values, we had to have data, because a p-value was how likely is it that we could randomly have data that's as extreme or more extreme than the data we've been given. So you needed data. Okay. But we never took a significance level into account, because we calculated p-values long before we even defined what a significance level was. All right. Well, to compute a critical region, you needed to be provided with a significance level, right? That's how we defined the critical region, in fact. But we required no data. So like on the very first panel of this video, I didn't give you any data. I gave you a random sample, but I didn't actually give you any kind of data for it, right? Okay, so let's go back and look at an example here. Earlier in this chapter, we looked at a coffee dispenser, which should have dispensed 7 ounces of coffee per cup. We didn't believe it. We tested it by drawing 15 samples from it. And of those 15 samples, we got a sample mean of 6.6 and a standard error of 0.8 ounces, okay? We then set up a null hypothesis that the average was 7 as the average manufacturer advertised, and the alternate hypothesis that the mean was less than 7. And we obtained a p-value of 0.0366. Look back at your notes, okay? All right, never set a significance level, but there's our p-value. All right, well, now how do we do this with a critical region, okay? Maybe I wish to determine whether I should accept or reject the null hypothesis based on a critical region argument. So let's set a significance level of alpha equals 0.05. I'm comfortable rejecting the null hypothesis when I shouldn't have 5% of the time or less, okay? So 0.05 is the probability that I reject the null hypothesis, given that the null hypothesis was correct. I'm going to reject the null hypothesis if my sample mean is less than some threshold, because my alternate hypothesis was that mu was less than 7. So how far below 7 do I have to look to reject the null hypothesis? Okay. All right, well, I'm going to standardize both sides. I'm going to subtract from x bar and c the 7, because that's the null hypothesis is correct. So subtract the 7, divide by this, the standard error over 15. And now this doesn't create a standard normal variable. This creates a t variable because remember, I didn't know the standard deviation of this distribution. I estimated it with our sample standard deviation. So I'm creating a t statistic now on the left. The right, I've got all that junk. However, for a t distribution, since sigma wasn't known, we've got 15 minus 1, 14 degrees of freedom, and I'm looking for the 0.05 quantile, right? The 0.05 quantile for it. And it turns out via R that I got negative 1.76131. So I set negative 1.76131 equal to this monstrosity, C minus 7 over 0.8 divided by root 15. Solve for C, and I get 6.6362. So a critical region, a significance level / critical region argument says I should reject the null hypothesis if my sample mean is less than that C value. Our sample mean was 6.6, which is less than C value. So our critical region argument would say that we should reject the null hypothesis as well, as did the p-value arguments, as long as we have a p-value of 0.05 or so, right? But these were very different arguments we did to test whether or not to accept or reject the null hypothesis, right? So critical regions and p-values, very different objects, okay? If you know what the p-value tells you to do, you don't necessarily know what the critical region argument would tell you what to do with the null hypothesis to accept it or reject it.